All right, so we started chapter 6 by taking a look at the kinematics involved in circular motion. Now, the next thing that we'll look at is we're actually going to start to evaluate the dynamics or the forces involved in circular motion. So, pre-lecture video 2 is your first introduction into that. In this video, there's 3 different examples that he talks about. He talks about a car going around a portion of a semicircle. So if I were to think about, here's my curve, and the car as it's right there, if I were to draw a free body diagram, there has to be some acceleration towards the center of the circle, which means there's a net force to the center of the circle. And he talks about how that's the force of static friction. And then he also talks about the frontwards view, and we could think about that as like a runner as they're going around the circle in a track, and how there's this natural tendency, sorry, it's not quite working, not quite what I wanted it to be, but as they go around the track, there's a natural tendency to lean, and that's because there's a normal force going up and to the right because your weight is going down, and you need this static friction to help you turn. And it's the same thing with the car. So he gets into a little bit of the free body diagrams behind going around the radius of curvature, both in a car and as well as running. Then he evaluates one last type, which is what if we're going over a hill. So we'll take a look at hills and we'll take a look at dips. And these are portions of semicircles as well. So if I'm at the top of a hill, my acceleration is towards the center, so my weight has to be larger than my normal force. And if I'm going around a dip, again, center of curvature, so now my normal force has to be larger than my weight. But when I take a look at these two examples, I get different feelings of weight and apparent weight. And we'll talk about those throughout this chapter as well. Okay, so the next section of chapter 6 is dealing with dynamics of circular motion, specifically of uniform circular motion. It says part 1 here. We're actually going to combine this into one section, and it's actually pretty quick because we do have some partner problems and stuff that we'll take a look at, but we'll do those during class. So we're looking at dynamics of uniform circular motion, or the forces involved with circular motion. So here is, again, our picture of something going around the track now, or going around a circle over on the right over here. So we already drew this kind of last section, but that means if there's an acceleration towards the center of the circle, that means there has to be a net force to the center of the circle as well. And that net force, as you see on the left, net force is always mass times acceleration. Well, acceleration, we said, was v squared over r. So the net force is mv squared over r toward the center of the circle. This is not a new kind of force, but it's still that net force. It's going to be caused by another force. It can be caused by tension, like when I have my keys spinning around, friction, like if I'm making a turn, or even the normal force. That's also can help me provide this centripetal force. So we'll talk about the concept of the centripetal force as we go through this chapter, but this is taking a look at when I have centripetal acceleration, there has to be some type of force that's causing it. And the magnitude of that force is mv squared over r. So I got a quick check. A ball is at the end of a string being swung in a horizontal circle. So if I were to kind of draw that out real quick, that's me holding a string out to the side, and then it's kind of swirling around above the ground. And the question is, what force is producing this centripetal acceleration? It's going to be the tension in the string. The tension is what's causing it to stop. If I let go of the string, this would fly off to the side because that tension is no longer there. All right, another quick check. The ball is at the end of the string being swung in a horizontal circle. The direction of the net force, the acceleration is always towards the center of the circle, so the force is also always towards the center of the circle. So this is a quick little video. It's kind of silly. Self-mowing lawn. We have a lawnmower on a string. So the lawnmower just wants to go forward at a constant velocity. So the string is providing a tension that causes this uniform circular motion. And as you can see, we got these nice centripetal circles, or what's the word? Centric circles? Yeah, that his lawn is mowed with. So it's a silly little video that demonstrates that. Another quick check. Hockey puck is tied to a string, but to a stake in the ice. The puck is then swung in a circle. Force is producing this centripetal acceleration. Again, it's going to be this rope right here. There's this tension that's causing that to go in a circle. Another quick check. The coin's rotating on the turntable. It moves without sliding. That's the instance shown, which following gives the directions of the following. So right now it's rotating counterclockwise, this direction. So the instantaneous velocity is going to be right here. It's going in this direction. That's point A. The frictional force is actually kind of a weird thing to think about, but it would go forward, and there's a direction of an acceleration, and that's towards the center of the circle. So this D right here is actually the direction of the frictional force, which in this case is providing the centripetal acceleration. And then if all of a sudden I got rid of this frictional force, then the instantaneous velocity, which is A right here, is going to be the direction of motion. All right, so we got a quick little conceptual example, and we're going to take a look at this more later, but it says engineers design curves on roads to be segments of semicircles, or circles. They also design dips and peaks to be segments of circles with a radius that depends on expected speeds and other factors. So when you engineer a road, how tightly it turns is very carefully thought about. It says a car is moving at constant speed and goes into a dip on the road. At the bottom of the dip is the normal force of the road on the car greater than or less than or equal to the car's weight. So if we were to take a look at a free body diagram of this, we can see that at the dip of the road, and this is obviously way over exaggerated, there has to be an acceleration upward. If there's an acceleration upward, that means that there also has to be a net force upward, because if the acceleration is towards the center of the circle, then the net force must also be towards the center of the circle. And if that's the case, then the normal force has to be larger than the weight of the car. And how do you feel when this happens? Well, you can think about it as like on a loop-de-loop. And on a roller coaster, at the bottom of that loop, you feel like you're being compressed. You feel very, very heavy. And that's because you have a larger normal force. And as we learned in chapter 4 and chapter 5, the normal force is equal to your apparent weight. So if you have a larger normal force, you also have a larger apparent weight. So this is just summing it up. Again, your normal force is larger than your weight, so you appear heavier. Now there's another example. What about if we're going around a turn, and let's get a top view of going around a turn. It's turning a corner at a constant speed while following the segment of the circle. What force is necessary to provide that centripetal acceleration? So the centripetal acceleration has to be in towards the center of the circle. And my question is, what force is providing that? And we know that there's a net force because there's acceleration. And he talks about this in the pre-lecture video, but the force that's allowing the car to make the turn is the force of static friction. And you might think that that's weird because it's not stationary. But if the car was turning without static friction, it would slide, and then it actually wouldn't be able to turn. So kinetic friction is actually what makes drifting possible. So it's the tire slides side to side during drifting, but when turning, it doesn't slide at all. So it's static friction. A great example of that is hydroplaning, and there's a lot of videos out on YouTube, and I've seen some are better than others, but the concept of hydroplaning is I'm going at some velocity, and due to a lack of friction, my car starts essentially drifting. And what that means is that I have broken static friction. So you might experience this, especially when it's heavy rain, especially when it first starts raining. When you experience it is when you're accelerating. So in some of these videos, you see people taking turns, and that's when they start losing it because they need that centripetal acceleration and that static friction to allow them to turn. So a really interesting application of losing that force of static friction. All right, we got a quick check. A hollow tube lies flat on a table. So this is actually a view from above. It's kind of misleading. This is a top-down view. The ball is shot through the tube, so it's coming around. What happens when it leaves the tube? Well, the instantaneous velocity is this direction, so it's going to follow path C. Now, it can't follow paths B or A because all the way through as it's going around, it's pushing against the wall. So there's actually a normal force that's pushing it into the center of the circle, and that's what's causing that centripetal acceleration. Once we get rid of that by losing the wall, it's just going to go straight. It's going to go in the direction of its instantaneous velocity. All right, so we got a real example, and this is the hammer throw. And in the track and field event known as a hammer throw, athletes spin a heavy mass in a circle at the end of the chain. Once the mass gets moving at a different speed, the athlete lets go, and then it follows in a parabolic arc. So the person actually stands here, and they hold this chain that's attached to this really heavy object, and they spin around in a circle, and they let it go. And when they let it go, the instantaneous velocity goes off into the instantaneous velocity goes off into whatever direction it was being thrown at, and then it follows this nice trajectory similar to a projectile motion problem. So it says that the hammer is a mass of 7.3 kilograms at the end of a 1.2 meter chain, and it says a world-class thrower can get the hammer to a top speed or instantaneous velocity of 29 meters per second. And if they're swinging it in a horizontal circle, what's the tension in the chain? And well, the tension is what's providing the net force and the centripetal acceleration. So that's equal to mv squared over r. And if I plug that in, that's about 5,100 newtons. That's the same as holding a 510 kilogram mass, which is 1,000 pounds. The people who do the hammer throw have to have huge strength to get that velocity. So imagine, you keep spinning it faster and faster. It appears heavier and heavier. And when you get to this big of a speed, you get to that huge force, which is really hard to hang on to, which is why it's a tough event. This is a quick video. It's from the slow-mo guys, and they experiment with spinning a CD at faster and faster and faster RPMs, and that centripetal acceleration causes what we like to call, we'll talk about more later, a centrifugal force, and that's based on mv squared over r. So the faster you spin something, the greater the force it experiences. This gets into like the human centrifuge and a couple different applications that we'll talk about this unit. But they spin a CD faster and faster until it breaks, and then they take a look at the slow motion video of it breaking. So it's kind of a cool video, worth kind of skimming through. I don't know if I'd watch the whole video, but definitely worth a quick skim. So to recap, we have this net force. The net force is what's causing the centripetal acceleration, so I like putting that little subscript C, and that's mv squared over r, which is towards the center of the circle. So your first partner problem, which we'll take a look at in class tomorrow, it says what's the maximum speed at which a 1,500 kilogram car can make a turn around a curve of radius 20 meters on a level road without sliding. It says note the coefficient of kinetic friction is 0.8 and static friction is 1.0. Well, we said before that the coefficient of kinetic friction only matters if it's drifting. So I'm actually going to use the coefficient of static friction. And we'll take a look at this problem in class tomorrow, but we're taking a look at what causes the car to be able to turn. And engineers can actually use this formula to determine, based on a road, what the speed limit should be. So when you see those yellow cautionary speed signs, those are based on road conditions. And if you're something like a civil engineer and you have to determine those, you have to take a look at static friction and how that affects you. So we will take a look at this problem tomorrow during class. The answer is in the notes, but we'll talk about it more tomorrow. So here's another example problem, and this is very, very, very similar to the previous problem. So I'm not going to talk about it too much right now. It's actually a very specific example, but now we're on a banked road. And the question is, at what speed can I make the turn without the assistance from friction? And we just said that the car needs static friction to turn. But let's take a look at this problem real quick. Here, I have the normal force is coming off of the surface, which means that there's actually an X component of the normal force. So if I'm on a banked road, I actually don't just need friction to cause it to turn. There's this X component of the normal force that can allow me to turn. So when people calculate how fast they can turn, an example for like a NASCAR race, they take into account the radius or the bank of the road, and then they can increase their allocated velocity to go faster around that corner. So when you watch like a NASCAR race, as boring as it could be, they have everything calculated to their optimal velocities when they go around the track. There's a crazy amount of physics involved with that. So this is just going to go through the math behind it. So in the X direction, I have the X component of the normal force. In the Y direction, I had the Y component of the normal force and the weight. It's not accelerating up or down, so the net force in the Y direction is 0. The X direction is causing my centripetal acceleration. So the normal force equals the weight divided by the cosine theta, which is mg over cosine theta. And if I plug that into the other direction, this is the X component of the weight, that turns into mg tan theta, and that equals mv squared over r. The masses cancel, and the velocity is the square root of rg tan theta, and I get this maximum velocity. It's not important that you know how to do this problem. It's just a really great example of how we can determine those things based on the centripetal acceleration. So I went through that really quick. Again, I would never have you solve a problem like this. It's just a cool application. So we got another partner problem that we'll take a look at tomorrow, and this will be the last one. It says wind turbine, it's spinning, it's got 1,200 kilogram blades. They're 38 meters long. The blades spin at 22 revolutions per minute. And if we model a blade as a mass at the midpoint of the blade, what's the inward force necessary to provide each blade's centripetal acceleration? So we're just taking a look at what is the centripetal acceleration, what's the magnitude of it, and we'll take a look at that tomorrow. And that actually concludes our introduction into solving circular motion problems. Next, we'll take a look at the apparent forces, and we'll take a closer look at that net force concept of the F net is mv squared over r. And we're going to take a look at some of the applications as it appears or contributes to your apparent weight. So we'll do that in the next segment.